name is Ken Russell. I am actually not Neil Trevitt, not the president of the Kronos Group, but I am the chair of the WebGL Working Group. I will be presenting Neil's slides, given that he is in Dublin for a Kronos face-to-face meeting. And the topic that I would like to talk to you about today is the ecosystem around WebGL and WebCL, which are two of the graphical and compute acceleration APIs that Kronos is developing for the web. So the topics that we'll go over, first we'll do a very quick introduction to 3D. I mean, has anyone programmed using 3D graphics before here in the audience? Small percentage, like one person, okay. So we'll break down a little bit how the 3D pipeline works, talk about the need for accelerating APIs like 3D, like WebCL, and then go into a little bit more about what exactly these APIs provide to the web ecosystem. We'll talk a little bit about WebGL tools and frameworks that help developers that aren't too experienced with 3D graphics actually get stuff onto the web quite easily. And then we'll talk a little bit about going from 3D graphics to actually lower level computation and how WebCL can accelerate these sorts of computations in the web browser. And then talk a little bit about, actually, it's Neil's favorite topic, and it's also a pretty cool one. What if we could do augmented reality applications in the web browser, and what would that entail? What would that take? And then we can have plenty of time for questions. And my colleague Zhenyao Mo from Google, who also works on the WebGL implementation in Chrome, will next talk about WebGL in more detail, showing you exactly how you can construct a very simple scene from nothing to having at least a shaded triangle on the screen, and possibly more topics. We haven't actually synced up on all of the slides that he will be presenting today. So, question number one. What is real-time 3D graphics? I mean, you've all seen it in the movies. Every film that comes out nowadays has CGI for all of the special effects. They really don't like to put actors at risk anymore nowadays, falling off horses or anything like that. All of this stuff is done in the safety of a studio with plenty of crash pads around, and then computer graphics is added later to make it look realistic. Anybody play games, computer games? Okay, there it is. Pretty much every game that comes out today on PCs, on mobile, on consoles has some element of 3D. Even if it's only a 2D game, you typically have parallax and other effects done using 3D effects, using multiple planes that are whose textures are uploaded to the graphics processor and who are translated around using commands that are sent down to the GPU. So 3D graphics fundamentally is the science and art of using computers to create and enjoy beautiful and interactive experiences. And the piece of silicon that makes this possible in real time is the graphics processing unit, or the GPU. And did anybody here play Doom when it came out? I mean, I loved Doom. When I was in college, we hacked Doom to death. Not only did we play it a lot late at night, but we also took apart the level files and did things with them. So we had the privilege of having some silicon graphics machines, which were the top-end graphics processors, really super fast CPUs, central processing units, that you could do a lot of physics and other kinds of simulation, as well as amazing graphics pipelines. And this is, they were the genesis of the entire 3D ecosystem today. So we took Doom apart and took the level data and did things with it, like put the user, you the person, into the Doom environment, or put virtual interactive creatures into the Doom environment and had them wandering around. So not just monsters and chainsaws, but actually like dogs and cats and hamsters wandering around the halls of these huge Doom levels. And it was a blast, but the techniques were fairly limited. It was fairly limited what you could do back then, because all the 3D actually had to be done on the central processing unit, at least on PCs, and that's why Doom's visual effects were kind of blocky. And then Doom for GL came out, where it was actually running on the graphics processor and silicon graphics machines, and that was another major step forward in terms of speed and in terms of quality. And since then, Quake came out and a ton of other games, and nowadays you see the Samaritan demo that was shown at I think that was at SIGGRAPH 2011, and it's just incredible. This is running on, like, I think 2 Fermi cards from NVIDIA. I mean, it takes that much graphical processing power, the two highest end cards side by side, in order to get these amazing lighting effects. But the ecosystem has just evolved dramatically. And the effects that are possible, even on a mobile phone today, are pretty amazing. And we'll show some examples in a bit. Now, and what's super cool, by the way, is that this is all real time. You can do these kinds of effects at 60 frames a second. That's what's so cool about it. You can imagine an effect that you want to put in front of the end user, and you can get it to them. You can deliver it to them over the web, as we'll discuss, and get some amazing visual effects that run on every kind of computer out there, be it a handheld cell phone or a high-end workstation. So what's 3D? Basically, 3D is a bit of a cheat, okay? It's an art of faking what looks photorealistic by doing some, by using heuristics that have been developed over the years. The earliest sorts of 3D effects were fairly simple. First of all, you know that things that are closer to you appear bigger, things that are further away appear smaller. This is a very straightforward geometric relationship that is, I guess, technically called perspective projection, but you can actually draw, using just high school geometry, similar triangles showing the relationship of objects' perceived size depending on how far away they are from you. And it really just amounts to dividing by z. The farther away in the z coordinate the object is from you, the smaller it appears to be, because you're dividing by a larger and larger value as it goes away from you. So the earliest 3D was basically just taking the vertices of your 3D model, perspective projecting them, and then shading them in such a way that it looked like there was some kind of light effect going on. But the heuristics have dramatically increased over the years, and again, we'll touch on this a bit more. So there's usually some kind of a database or some stored representation of your 3D models. And the surfaces of the objects that you're going to be displaying on the screen are broken down into a grid of not just polygons, but actually triangles, okay? The triangle is the key element of 3D graphics. Does anyone know why the triangle is the key element of 3D graphics? Anyone? Anyone? It's actually a really simple answer. The triangle, as opposed to, say, a square or a quadrilateral, it's absolutely determined which plane that triangle lies in. I mean, the three corners of the triangle determine actually a plane in 3D space. If you have 4 points, it's a bit ambiguous. They don't necessarily have to lie in a plane. They can twist a little bit. And then you have to decide, okay, well, if I want to disambiguate what surface I'm trying to represent, do I connect this diagonal or do I connect that diagonal? Okay, this is why the triangle is used as the basic primitive on graphics processors, that there is no ambiguity about how it's going to be rendered, okay? How each of the points that are inside the triangle show up on the screen. So the surfaces of the 3D objects that are rendered with WebGL, with any of these APIs, are broken down into a grid of triangles, a mesh of triangles. And the points of the triangles live in a 3D coordinate system, 3D space. In the previous fixed function 3D ecosystem, and we'll talk about what that was and where we are now, you would associate a material with each vertex. You'd say, this is blue, or it's shiny, or something like that. And the graphics card would figure out how that vertex was supposed to be colored, depending on that information. So for example, if you have a blue vertex out here, and it's not shiny, and you have a white light source pointing at it, it's going to be blue because the white light source is illuminating this diffuse blue point. Excuse me. But if the vertex is shiny, you may get a bit of a glint coming off of the light source, right? Okay, and for that reason, the vertex would actually show up white, not blue, which is interesting, right? So you get different visual effects depending on the kinds of materials you apply to the 3D models that you're displaying. And finally, the vertices, of course, are positioned in a 3D coordinate system, right? This is the typical thing that you do when you're a computer graphics programmer. You make your right-handed coordinate system, positive x, positive y, positive z, and then you position your your objects in the scene. And it's linear algebra, it's matrix math that allows you to represent how these objects move around in the scene. Okay? So, how does it work? The first thing that's done is, on a per triangle basis, the graphics card projects the vertices of the triangle onto the screen. Typically, there are two matrices involved in this. One is well, maybe three. One is typically called the model matrix, and the model matrix moves, conceptually anyway, moves your object around in the 3D space. Okay? Then there's the viewing matrix. The viewing matrix decides where the camera that's viewing all of the objects in the scene is supposed to be placed. And then finally, there's the projection matrix. And the projection matrix warps space in this way that we talked about. You know, it gives you the perspective projection. And there are different projections that you might choose. For example, you might want orthographic projection. An orthographic projection is extremely useful for computer-aided design. Okay? And it's a different view because it doesn't actually have the foreshortening that the real world does with perspective projection. There are other two-point perspective projections that are really useful in architecture, where you have actually two vanishing points, not just one. And all of these can be represented using the appropriate projection matrices. But once you've multiplied using just linear algebra the vertices of your models through these matrices, what you ultimately get is points in 2D. Okay? And it's basically -1, so 1 by 1. It's a unit, or maybe 2 times unit coordinate system. And that's ultimately what OpenGL and what WebGL work with. And so ultimately, they boil down to a 2D graphics API, believe it or not. Anyway, once you have the triangles on the screen, okay, you have to figure out which dots, which pixels are going to be colored in. And that's what the GPU does, part of what the GPU does. All right. Now, once we've figured out which points, which pixels we're going to color, we have to figure out how we're going to color them. And this is where the shading techniques and some of the other heuristic tricks that have been developed in the 3D space come in. So for example, with smooth shading, typically what you do is you take the points of the triangles and you figure out what the color is supposed to be at those 3 points. It's going to be different, right? Because each of these points is at a different location relative to the light source, for example. You know, maybe this point on this triangle is closer and this one is farther away. And they're pointing in different directions, so they're going to get shaded differently. This one is going to be brighter because it's pointing at the light source. This one's going to be not as bright because it's pointing away from it. So in smooth shading, you compute the lighting at each vertex, and then you interpolate the colors of the vertices across the triangle. Okay? There are techniques for getting enhanced realism at a low cost, like texture mapping, where you take an image and you wrap it around your 3D model. Okay? This was one of the first techniques that was developed on Silicon Graphics workstations to dramatically improve the realism of the scenes that you were looking at, because you didn't have to send down a lot more triangles in order to get something that looked much more visually realistic. And environment mapping is another nifty trick, and we can show a demo later, where you actually consider your object to be living in a space, and the space is defined by an image, or actually a set of images. So you put your objects in a box, and you consider the objects to be reflective. And environment mapping, when it's rendering the triangles, it'll bounce a ray off the object and figure out what part of the environment is being reflected off it and hitting the eye, and it gives you a very, very compelling, realistic-looking mirrored object. And these were some of the techniques that were developed in the early days of Silicon Graphics workstations. So, what happens when we're rendering our triangles? The pipeline basically goes in the top down here. First, we traverse our object representation, our scene database, and figure out what we're going to be rendering. The representations differ dramatically depending on whether you're doing a real-time game, whether you're doing some kind of an architectural or CAD application, but fundamentally you have a bunch of 3D objects that you're going to be rendering, and you have to iterate down them to figure out what you're putting on the screen. Then you transform them. Okay, you move them into their appropriate place in 3D. Then you say, okay, well, based on their current locations in 3D and the current positions of the lights in the scene, how are they shaded, okay? And then finally, they're rasterized. They're converted from you know, a vector representation where they're just 3 points in space, and they're actually converted into what pixels are going to be filled in on the screen, okay? So this is sort of the geometry phase of the pipeline, and then there is the rasterization phase of the graphics pipeline, where the actual pixel-by-pixel operations are executed. For example, interpolating the colors of each of the vertices of the triangles, okay, to get the right smooth result, figuring out which dots on the screen are actually visible, because these triangles, if you consider my laptop screen to be the edge of the screen, the triangle might go off screen, okay? And then this vertex down here wouldn't actually be visible, so the triangle would be clipped to the edge of the screen. And then finally, the pixels are actually written to the screen, to the frame buffer. So here are a couple of diagrams of actual 3D pipelines. And for comparison, we're going to show what the mobile phones used to look like, which is on the left, and what mobile phones today look like, which is on the right. So on the left is mobile phones from, I don't know, vintage early 2000, 2001, 2002. These mimicked the 3D functionality that was on desktop PCs at the time, okay? And it had heuristics like lighting, texture mapping, environment mapping. They had a little bit of additional fog, for example. They had, you can actually see these stages, by the way, in here. So if you can see my mouse, this is the part of the pipeline that would implement the fog function, all right? There was actually a special purpose thing in the graphics pipeline that would compute fog to give you a little more realism in terrain rendering, for example. But it was very, very specialized, right? I mean, if you're indoors, for example, you don't need fog, right? So the previous pipelines were a collection of heuristics that allowed you to get pretty compelling looking graphics. And it was realized that it wasn't enough, because the people who were designing these pipelines couldn't come up with all the ideas that the graphics programmers wanted to put in practice, right? All the visual techniques that they wanted to achieve. So the major shift that occurred some years ago is the introduction of the programmable graphics pipeline. Now you can actually write a small snippet of computer code and upload it onto the graphics card and have the graphics card run it, and that is how it figures out how the pixels are shaded on the screen. This is really cool. This is what WebGL is built on. This is what all smartphones today are shipping with. It's called OpenGL ES 2.0. And this shift from the old fixed function pipeline paradigm to the programmable graphics pipeline was a major, major paradigm shift. It was an incompatible API shift. So basically, old applications had to be rewritten for the new API structure, but it gives you much, much more control over how your 3D scene works, how your pixels are shaded, and it lets you do amazing effects that you could not possibly do with the fixed function pipeline, and we're going to show some examples of that in a bit. So now I have to step back and put on my business hat for Neil and talk about a little what the Kronos Group actually does. So the Kronos Group is the organization that develops OpenGL and develops OpenGL ES. These are the standard 3D graphics APIs that run across multiple platforms like Linux and Mac and Windows. And they're creating open and royalty-free acceleration API standards, okay? And their focus is on graphics, it's on audio, it's on really any kind of dynamic media, either input or output. And we'll talk more about all of the stuff that's going on in the Kronos Group in a bit. And the Kronos Group tries to develop APIs that are very low level, okay? Just above the silicon, just above the lowest level graphics driver. Because historically, there's never been any agreement on higher level 3D graphics APIs, although there's been some miraculous 3D graphics APIs developed over the years. SGI, Silicon Graphics, had a couple of wonderful libraries called Open Inventor and Performer. I used both of them back in the day, and they were just a pleasure to write program code for. They were easy to use, easy to get 3D graphics on the screen. But unfortunately, for some reason, and I think the reason is that they don't they don't admit enough use cases, fundamentally. They don't allow you to write maybe highest performing games on them because they're not targeted for the game model representation. They didn't succeed. But OpenGL tries to be just a layer above the graphics hardware, and then any other higher level APIs that you want to build, the application is responsible for doing it. And this has succeeded, that paradigm, that technique. So Khronos tries to target the lowest level APIs so that they will have the most, the highest applicability to applications. And Khronos, by the way, is also an industry cooperation consortium. Okay, any company can join it. There is an IP framework to protect members from, to allow safe development of intellectual property. So you can have like a 2-year time window for development of an actual graphics chip, and collaborate with others that are in the Khronos group, and that IP will stay safe within the Khronos group. So there are a lot of members. Again, any company is welcome to join. If you are an open source software developer and you have something strong to contribute, I actually think that the Khronos group would be open to possibly waiving the membership fees. But a lot of industry participation. And by the way, it's a very unique forum because, for example, in the development of WebGL, the browser vendors can talk directly to the graphics chip makers. We can say, okay, NVIDIA, AMD, here are some constraints that we're under. Can you please make your graphics chips work in such a way so that we can make the web API work better? And these things happen. These sort of synergistic relationships actually happen within Khronos. So some of the things that Khronos is developing today, WebGL's down there. We'll talk about that. WebGL is built on OpenGL and OpenGL ES, the two C-based 3D APIs for, again, multiple platforms. There is a standard for doing vector graphics, OpenVG. There is a new standard for doing high-performance, low-latency audio called OpenSL and OpenSL ES. The Collada format is developed by Khronos as well. This is an industry standard interchange format for moving 3D models from one application to another. And there's some interest, OpenCL, how could I forget, the ability to use the graphics processor, which is a real high-performance floating point machine for general purpose computation. So you can do matrix math, physical simulation very, very quickly on your home PC. And one of the new forays that Khronos has made is called Stream Input, which is a really, really cool input API that tries to define semantics for different kinds of inputs that you might receive into your application, and lets the application negotiate what it wants to receive from, say, the phone, because the phone actually has a lot of sensors in it, and you want those sensors to feed an input into your 3D game that you're running, hopefully in WebGL in the browser on the phone. So Khronos develops all of these kinds of standards to meet real market needs and help drive industry adoption across multiple platforms. So ultimately, you're trying to drive user experience. You're trying to make some amazing visual experience or visual and audio and input experience that the user is going to remember. And the new mobile silicon that has advanced GPUs built in is the key thing, the key innovation over the past, say, 5 years that's really driving the ability to deploy these things everywhere, not just on a big workstation or a big desktop PC, but also things that you can take with you. So I'm pretty sure that this is the NVIDIA product line, okay, and expectations for acceleration as we go forward. But you can see that it's actually getting, like, performance is exponentially increasing on these mobile devices. The performance of a mobile phone today is dramatically higher than what it was just a few years ago. So the experiences that you develop on the desktop can now be run on a mobile phone. I mean, if you just think about the way that the computing industry in general has gone over the past 20 years, you had your Apple II a long time ago, and now you have a handheld cell phone that's like 1,000 times more powerful than it. It's amazing. And these are the kinds of performance increases that we're seeing in mobile GPUs nowadays. This is neat because it really lets you write your 3D application once, deploy it on the web, and run it everywhere. So NVIDIA in particular, and the Khronos group in particular, are interested in in getting these experiences wrapped up in the web so that we can collectively write our applications and deploy them everywhere, okay? And the question is, how can the web browser actually pull in all of these features, like rich audio, rich graphics, input devices, cameras, computer vision, all into one experience? How can the web browser be the vehicle for deploying all of these kinds of portions of the experience? So let's talk about each of the subcomponents in a little more detail. First of all, OpenGL ES, which is what WebGL is built on, is the OpenGL subset that was designed for mobile and embedded devices. OpenGL ES, even the 1.0 version, but in particular the 2.0 version, erased all of the legacy APIs from the 3D development over the past 15 years. And it got down to the real core of it. Like, what do you really need in order to put triangles on the screen and control their pixel colors, that you can get amazing visual effects? OpenGL ES2, which is what WebGL is built on, is that API. And it actually is now the dominant API for mobile devices. Pretty much any device that you see shipping with, say, the Android operating system, the RIM playbook, the Apple, iPad, and iPhone are all built around the OpenGL ES standard. So this is the one API. If you need to learn one API this year, I would recommend that you learn OpenGL ES, because it will let you write 3D applications for all of these devices. And it doesn't matter the language that you're writing in, really. You have to just understand the API and its semantics. And OpenGL, by the way, is the basis for many high-end content and engines, such as id Software's Rage, Unity, Unreal Engine, for example. So we already discussed this, but basically the OpenGL ES2 programmable pipeline erased a ton of legacy from the 1.0 pipeline and gave you the ability to write a piece of program code that runs, it's actually two pieces of program code, one which runs on every point of your triangles and one which runs on every pixel that those triangles cover on the screen. And those two abilities, the ability to move your points around in 3D space and then control exactly how they're colored, are the two key elements of being able to develop really amazing looking 3D scenes. So what's WebGL? WebGL brings the OpenGL ES2 API to the web. It brings three-dimensional graphics to the web without any browser plugin. Does anybody remember VRML from back in the day, 1995 era? A few of us, all right. It's not maybe a brand new concept. It was tried 15 years ago, but VRML really didn't take off. And there's plenty of guesses about why that might have been the case. But in my opinion, WebGL is actually quite different. It's a different situation. It brings a lower level API to the web, one which everybody can build on top of and make more powerful libraries, more powerful experiences. And fundamentally, the JavaScript engines of the web browser have gotten a lot faster since 1995. And that lets you write much more application code and customize its behavior in ways that you couldn't do with VRML, because VRML was a bunch of fairly big building blocks. But with WebGL, the building blocks are much smaller, and you can put them together. You can put many more of them together in your application. So basically, your application can be much more customized than it could have been 15, 20 years ago with the VRML solution. That's why I think that this is going to work, and why it already is working. And it is bringing accelerated 3D graphics to the web. There's no question about that. There are lots and lots of demos, and I'm going to show you some of them today and show you where to find more. So WebGL hooks into the HTML5 canvas element and interoperates pretty cleanly with all the other DOM content that you have on your page. So in addition to being able to overlay and underlay text and build your UIs in HTML, you can also bring in images from your web page and use them as textures in your 3D scene. So it builds on top of the infrastructure that's in the web browser. And so the convergence of things like faster JavaScript engines, wide availability of OpenGL ES2, and multiple browsers running on multiple platforms really makes this the time that I think this is going to succeed as a concept. 3D on the web. Just go to a web page and you have this amazing interactive experience. So there's an ecosystem around WebGL, and it's really interesting. This is a cool diagram of what's actually going on in the working groups. So on the desktop side, the OpenGL architecture review board evolves the capabilities of the graphics processors that you see in workstations and in PCs, okay? So the leading edge functionality typically does come out on desktops. Then these ideas come down into the OpenGL ES working group, okay, from OpenGL. And they're distilled down and maybe simplified, maybe some features are removed so that the API can remain simple and the silicon can be simpler on mobile phones. But that's what shows up on your smartphones. And that direction of flow of ideas is what happened and what allowed OpenGL ES2 to develop, shader-based graphics for your phone. And WebGL is building on OpenGL ES so that as the phones evolve in capability, so will WebGL, and also so that WebGL will run on all of these devices. So WebGL exposes the semantics of what's on your mobile phone, even on the desktop. So it doesn't expose everything that you can do with your desktop graphics card. But the wonderful advantage is that if you write to WebGL, your content will run on the mobile phone. You don't have to write 3 applications for desktop, for iPhone, for Android. You write it once on the web. It's simple to deploy, runs everywhere. Reach millions, hundreds of millions of users. That's the promise. And let me point out, by the way, that OpenGL ES has fed ideas back to OpenGL, okay, to define a core profile of the API that removes legacy features, that there's one very simple way of doing every operation that the 3D card can do. And WebGL is feeding back into OpenGL by way of informing the creation of necessary security properties so that you can safely go to any web page and run 3D content and know that it's not going to mess up your machine in any way. So there's a real nice feedback loop between all of these APIs, and it's really going on. This is actually happening. We have almost daily conversations between these working groups, and things are evolving. And I'll show you how to find the WebGL working group list, but I would definitely encourage you to follow these discussions if you're interested in how these APIs are progressing. So, what does WebGL look like inside? Okay. It's a fairly large stack of software. You have this web browser, right? And what's a web browser? It's a large amount of code to do layout and rendering and interaction, all these things. And WebGL hooks into this. So at the bottom level, when we work our way up, you have the OpenGL implementation on the desktop PC or on your mobile phone, the OpenGL ES implementation on your mobile phone. Okay, that's what the GPU vendors provide. This is what NVIDIA provides, what AMD provides, what Intel provides, what all of the mobile vendors like Imagination Technologies and PowerVR. This is what they provide. I should point out that on Windows, Chrome at least, and also Firefox are using a translation library currently to work around the fact that some of the desktop PC OEMs don't actually ship a viable OpenGL. So WebGL can even run on top of Direct3D today using the Engel translation library. So anyway, once you have the graphics library at the very bottom, then the web browser actually provides WebGL to you. There's a lot of C++ code involved to get WebGL rendering into an HTML canvas element and making it go fast. Okay? No plugins required. This runs today in Firefox, in Chrome. It runs in Safari with a little checkbox that you have to turn on, and it runs in Opera Next, Opera 12 that's coming out soon. Okay, so on the desktop, you got wide vendor support for this functionality. Once you got the web browser running, your application comes down in the form of an HTML5 web page with JavaScript. The JavaScript drives the WebGL API and makes your 3D models render and go. And there's plenty of middleware, by the way, plenty of 3D libraries that let non-expert 3D programmers get compelling, really nice-looking content that runs really fast on the screen with very little effort. 10 lines of code. You can have, a spinning textured box that you can actually interact with using your mouse pointer using 3.js. And I'm happy to provide pointers to these things. You can find them very easily. There are some links in the slide presentation, and certainly on the WebGL wiki, which is a good resource. So the way that the web page renders is a little bit different than the way that typical OpenGL applications used to render. Typically, you would just have a big window. You would do your drawing. There were two buffers, the back buffer and the front buffer. And in order to avoid seeing glitches as the triangles were drawn onto the screen, the OpenGL application would render into the back buffer. And then when it knew that it was done rendering this frame, it would say swap buffers. And then the back buffer would become the front buffer would become the back buffer. And at the next time the electron gun inside the CRT went to the top, that's when it would start to render the other buffer. Now, the web browser works completely differently. I mean, it's got its own composition architecture. So basically, the web page engine takes the HTML content that's on the page and makes a kind of a bitmap of it. Okay, it renders it into some picture. You may have video elements. You may have the canvas tag containing either 2D or 3D content via WebGL. And all of these images are actually represented as textures on the graphics processing unit, and they're drawn back to front so that you can get nice blending between them. And you can actually have multiple layers, which is cool. So you can have a background, gradient, and then your WebGL content, and then some text on top of it. And all of this stuff is just, all the rendering of this, the composition, is handled automatically by the web browser. You don't have to worry about it. All you got to worry about is making your nice 3D scene and writing HTML that gets all of the effects that you want. It's really cool, because back in the day, if you wanted to do text in OpenGL, it was a real difficult proposition. There were libraries, but by design, text is not part of the OpenGL API, but it is part of the web browser. So it's really easy to put text and other interactive elements on top of your 3D scene and build your entire UI in HTML, and it interacts seamlessly. That's cool. So, how does your WebGL content interact with the rest of the web page? Okay. As I mentioned, the 3D content can actually be, you can overlay and underlay the web page with your 3D. I would like to show you a demo. So let's hope that I can get back to exactly that web page. Okay, let's go to the WebGL wiki. Let's go to the demos. Let's go to this simple thing. Okay. Here's a shiny teapot, and it's sitting on top of a web page. So we can actually select the text of the HTML. And just by using absolute positioned HTML elements, you can get this visual effect trivially. Hey, look, it's 3D sitting on top of my web page. Easy, right? It's like 2 lines of code to make this work. Actually, since I'm no CSS expert, I was trying to figure out how to get the teapot to sit in the center of the text, and tried all these, autofill CSS rules, and wasn't able to get it. Finally, I just used the center tag, which any of you who do a lot of HTML will probably laugh at. And it worked from HTML 1.0 from 1994. But because the web has amazing backward compatibility, that still worked. And yet, you didn't think that you'd see that effect on a web page when they invented the center tag, right? So the center tag carries forward and actually allows you to position your 3D content in the way that you want, depending on the effect that you want. But the point is that it's really, really easy to get the 3D stuff to interoperate with the HTML. That's the high-level point here. Okay. So let's try this. So you can do your entire user interface in HTML. In fact, you can develop the user interface separately from your 3D app, and you can have one group of designers doing the UI and one group doing the 3D, and then you can just plug them together. You don't have to have them all working on the same code base. It's really, things interoperate really, really nicely. As I mentioned before, you can pull in other media content into WebGL. You can pull in video tags, you can pull in image tags, you can pull in other canvases, you can pull in other WebGL rendered canvases and use them as textures in your 3D scene so that you can wrap them around other objects or shade them or do embossing or other filters on the graphics processing unit so that it runs really fast. You can use 3D graphics for your web user interface. I mean, you could actually use a big canvas and render WebGL into it and get your mouse click events and figure out what objects you're hovering over, but then you can have the objects fly by as you go into a menu system that's actually deep as opposed to spread out all over the screen. So you can make really unique and very different kinds of user interfaces than you typically see on the web today, using WebGL and using the fact that you can interoperate with the web page around you. Okay, there's an experiment that both Google and Mozilla are working on. I'll show you a demo that lets you take a portion. Actually, it's really the entire web page, and get that rendered content into WebGL, so that you can then take your web pages and wrap them around, a cylinder or a sphere, or do crazy kinds of rippling effects or cloth simulations, and so these have security ramifications, unfortunately, but they can't be accessible from ordinary web pages. But if you trust the website that you're going to, it should be really, really seamless to write an application that does this sort of visual effect. So we're seeing some really nice back and forth interaction between 3D and the surrounding web environment. So let's talk about where it stands now, and I'll use this this opportunity to give an update on the current WebGL spec. So last March, the first version of the WebGL spec was introduced, called 1.0. And this was developed by 4 major browser vendors, Mozilla, Apple, Opera, and Google, working very, very closely with NVIDIA, AMD, Intel, and other GPU vendors in order to produce this specification that we believed was portable, that could run on mobile phones, it could run on Windows, and it could run on Mac and Linux, and it could run identically. Okay? And it actually was not trivial to do this, and if you want some more technical details, we can talk about the semantic differences between OpenGL ES and desktop OpenGL and some of the emulation that has to go on there. But anyway, the first version of the spec was released last year. That was a great step forward. Now, at the same time, or a couple months later, the typed array spec came out. Has anybody programmed with these on the web today? Typed arrays? Yeah, one person? Okay, so when we first developed WebGL, #1 problem was how do you get your vertex data onto the graphics card? Wasn't possible to do with JavaScript, because JavaScript arrays can hold any kind of object. They can hold numbers, they can hold strings, they can hold objects, they can hold undefined, they can hold null, anything you want goes right into a JavaScript array. They're great, but they're not efficient. So for OpenGL, you have to know exactly how your vertices are laid out. There's no question about it. You have to know that this is a floating point value, and the next thing to it is a floating point value, and then it's followed by 4 bytes, which are your color. All sorts of very low-level details are required in order to develop an OpenGL app. So the WebGL spec, or the WebGL working group, actually designed a typed array spec, and that allows you to talk about how you are laying out numeric data and giving it to, say, the graphics processing unit. And then it was split off in the WebGL spec because it seemed to be more generally useful than just WebGL. And now it seems that it's the standard for using binary data on the web, which is pretty awesome. So that was a nice, I don't know, contribution, say, from the WebGL ecosystem to the web. So the typed array spec came out around the same time last year, and there's some really cool stuff going on there too. One of the new things that has just come out is the ability to give to transfer data between threads. Anybody use web workers? Anybody? Write a web worker? Anybody? So a web worker is a JavaScript script where you can basically start up another thread in your web browser running a different piece of JavaScript. And you can use this post message API to send data back and forth between your worker and your main thread. So it's cool. And they're actually implemented with operating system threads. So you can give some work to the worker to do, and it can chew on it for a while without blocking your user interface, and then give the result back. The problem with workers is that because of their semantics, they cannot share data with the main thread. Okay, so you couldn't get efficient computation of lots of data and then give it to the main thread for rendering, for example. But the typed array spec had the opportunity to contribute there and solve this problem, and I think we did. We worked with basically all the browser vendors, including Microsoft, by the way, and slightly extended the semantics of the post message API for web workers to allow you to give a block of data to another worker, okay? So you've got your typed array, and you're holding onto this massive block of data, like, you know, tens and tens or hundreds of megabytes, and you say transfer, and the thing goes into like one of those you know, sliding drawers that you see at the bank. You know, you slide the thing in, and then the worker has access to the data, and you don't have access to it anymore, okay? And then when the worker's done producing its results, it transfers it back to you. And those transfer operations are zero copy and basically zero cost. That's cool, all right? So now you can actually do multiprocessing in JavaScript, and we've got some preliminary demos showing the speed ups that you can get by actually taking advantage of the multiple cores in your machine. And there's a lot of use cases for WebGL, like mesh downloading and decompression, image downloading, decompression, and transcoding. There's just some really cool new results in this area. You can do physics, lots and lots of amazing use cases, scenarios that you can reach with this functionality. That's in the typed array spec. So what have we been doing over the past year? The transferable support was actually part of that work, but there's a new version of WebGL coming out. We're calling it 1.0.1, and it fixes a lot of corner cases in the original spec. And it makes the spec much more portable. The behavior is much more tightly defined, and you're basically guaranteed that the WebGL implementation under your application is going to work the same across all these devices. So that's what's new. This is about to come out. We are focusing heavily on security. If anybody has questions about that, happy to field them. Fixing bugs and corner cases in the original conformance suite, and we're taking WebGL out from under the experimental flag. So you're just going to say get context to WebGL. Once multiple browsers are passing the conformance tests on multiple platforms, I must say that today we are waiting for OpenGL driver bug fixes in order to pass the conformance suite on at least 2 platforms. Getting closer though, okay? But these are bugs that have to be fixed that really can't be worked around in the WebGL implementation itself. And honestly, some of them are pretty long-standing. So anyway, once those bugs are fixed, we anticipate that going forward, you are going to see very, very predictable behavior of not only WebGL, but also OpenGL across a wide range of platforms, where previously there were a lot of corner cases that weren't actually covered, and where applications had to do workarounds. And so WebGL is feeding back into this, this ecosystem. If you take a look here, this table is a bit old, but if you go to caniuse.com, which shows all the HTML5 features and shows their deployment, WebGL is getting out there. So it's fairly widespread support, at least if you look at the numbers of web browsers that are supporting it. If you look at market share, there's a conspicuous absence of one particular browser that doesn't claim to support WebGL today. And I don't have anything more to say about that. All right, let's do another demo. So if you go to the, let me think here. What's the best way to find this? If you go to the WebGL wiki, and if you didn't see how I found that, you just go to WebGL wiki, or if you go to, say, some search engine, doesn't matter which one, WebGL wiki. Okay, the top hit is the WebGL public wiki on the Chronos site. And here you can go to, there's a lot of links. There are a few simple demos that we developed very early in the working group, but those aren't the interesting ones. If you go here to the user contributions, there's a ton of libraries, a ton of demos, a ton of just examples that show just incredible, incredible effects. So if we look for WebGL samples. Samples, yes. Okay, here we go. This project was actually mainly done by Mo's and my colleague Greg Tavares at Google. And he's got a bunch of really cool demos. Not all of them are 3D, by the way, and some of them show how to do like really fast 2D graphics using WebGL. The first one that he did was a response to Microsoft's IE fish tank demo. And you may remember that the IE fish tank was 2D fish, you know, wiggling around a little bit, flying around on the web page. This one is actually a 3D fish tank in a 3D space with light rays, fish, and sharks with laser beams that shoot out of their heads. You can see. So this is much more compelling. I think that this was developed in collaboration with Human Engines. I think they did the art assets and some of the rendering techniques for this. So it's a pretty canonical demo that we use for performance, actually, performance measurement. Because even though the scene is fairly complex, and you can see if we go to like 1,000 fish, you know, it's quite a lot of fish, it still runs at 60 frames a second, and it should. The graphics card is barely breathing hard doing this kind of content, which is really amazing. So WebGL is trying to expose this power of this graphics card to your application so you can develop cool content like this. And we're iterating on this and doing more and more advanced demos going forward. So anyway, all the source code for this is out there, so you can see the tricks that Greg did in order to achieve really good performance of these kinds of scenes. I'll show some more in a bit. Let me go back here. Okay. We already went there. User contributions on the WebGL wiki. Tons of stuff. 3.js is arguably the most popular WebGL library right now, and it's really easy to use. I mean, that was Mr. Doob, the original creator's point. Got to be easy to use. 10 lines of code. Got a 3D scene on the screen. That's the point. And it definitely achieves that goal. So, who wants to hear about WebGL Security? Okay, let's do it. I got more to talk about than is on this slide. So, there was a flurry of articles and activity around WebGL Security last summer. There was a little bit of truth and a lot of fear, uncertainty, and doubt. So let me clear the air here. The WebGL API is 100% secure. It is impossible to access memory that doesn't belong to you. Okay, out of bounds. This means out of bounds reads or writes, either on the CPU or on the graphics processing unit. And it's also impossible to access uninitialized memory, according to this API specification. And many of these assertions are tested thoroughly by the WebGL Conformance Suite, where the behavior is actually defined in such a way that you can test the results and make sure that the assertion is true. So these are properties of the specification. Okay? The spec says that if you index into an array in your vertex or your fragment shader, that you cannot go outside the bounds of that array that you're indexing. Now, OpenGL ES doesn't provide that guarantee, but the WebGL implementation does. This is the level of security that is implemented by the web browsers. So the only question that remains basically about WebGL security is, can you provide a really lousy user experience? Is it possible to, say, lock up your graphics card for a long period of time? Now, this is a long-standing problem in the graphics industry. The GPU doesn't multitask in the same way that central processing units do. So you can't go in and preemptively terminate a graphical operation that was submitted to the GPU. You basically have to wait for it to complete. But Microsoft actually innovated in this area and developed a mechanism for Windows that lets them reset the graphics card and the driver on demand. So if something goes dramatically wrong, you get maybe a 2-second hiccup in your user interface experience, and then the monitor powers off and comes back on and says, so-and-so graphics driver stopped responding and was restarted. Okay? That's the experience on Windows, and it's actually not bad. You get an application notification when that happens, and you can respond to it. So 2 things have happened. In the OpenGL ecosystem on Linux and Mac, specifications have been developed for basically accessing the same kind of functionality of resetting the graphics card if something bad happens. And these are being implemented today by GPU vendors, and some have already shipped this functionality. The web browsers have already incorporated the functionality. So Chrome, for example, watches for these graphics processor resets and does something in response. If it can be conclusively determined that WebGL was responsible, it's not going to run WebGL anymore for that web page. It's going to say, sorry, WebGL content on the web page caused the graphics card to reset, and that's a bad user experience, and we don't want that to happen to the end user. And this is an uncommon occurrence, but it's one that has to be guarded against. I mean, I'm sure we can all appreciate that we don't want, even by accident, to lock up our end users' machines, and certainly not, over and over again. So the web browser is defending against this, and we are going to be designing more, a slight additional amount of user UI in order to prevent a web page from repeatedly doing this. Okay, so basically, if it ever happens, we're going to prompt the user, put something up in the user interface saying, the graphics card reset or something like this, or WebGL stopped working. Do you want to continue? Yes or no? Try again, or no, thank you. So the user gets to decide whether or not they want to continue running the content. And as we discover actual driver bugs that are causing lockups like this, we are putting test cases in the WebGL conformance tests. This is a slightly tricky way of getting all of the GPU vendors to really make their drivers robust so that they can't get away with implementing some feature in a half-baked way that has the possibility of locking things up. They've got to make it work if they want to say that WebGL actually works on their GPU. And this is already having a very positive effect on the quality of graphics drivers. I can definitively state that. So anyway, the ARB robustness OpenGL extension is the key thing that is giving us the kill switch for the lowest level graphics operations, and then the web browsers are building more security on top of that. And we're really getting very close to conclusively solving this problem, and that to me is actually very exciting because it's a long-standing issue in the graphics industry. And if we solve it, then we can just, with great confidence, deploy amazing user experiences over the web. By the way, that last bullet point is correct. Longer term, the graphics processors will do multitasking, and then you can just, kill the rendering command in the same way that you could kill a process on a computer if it goes awry. So we've pretty much already discussed this. Did anybody hear specifically about the cross-domain image access problem that came out last summer about WebGL? Okay, yeah. Anyway, basically, issues that came up in this area have been conclusively solved, not only in the WebGL spec, but also the HTML specification. So basically, WebGL secure. Develop your content with confidence. Okay. I'm going to go a little faster through some of the rest of the slides because I want to get to some demos and questions. But the cool thing about developing your app for the web, as opposed to developing like an Android and iOS and some kind of, maybe it's a Steam game or something, is that you get to write your app once, you get to deploy it everywhere, and you get to use the wonderful infrastructure that's in the web browser to do not only your output in the form of text or buttons or something, but also to build your entire user experience using HTML. That's why it's cool. I'm privileged to have some colleagues who have developed some pretty cool WebGL content and they're, by the way, like longtime OpenGL hackers. And at least one of them said that WebGL was the best OpenGL development environment he'd ever used. He just hits shift reload and he sees the new JavaScript code that he wrote. And it is really cool. I mean, I did a lot of Java OpenGL work back in the day, and it was still painful to do the compile step, put the jar on the server, and then hit shift reload. Now you just edit it in your text editor, save it, shift reload. And the reload time is really, really fast because the JavaScript engines have been heavily optimized. So it's a great development environment. And there are amazing tools built into the browsers too. Another reason, again, that you would want to develop for the web as opposed to, say, an app store, again, you cover all the devices. You don't have to worry about different app stores for different devices. Even app stores for the web, you don't have to worry about it. You may have to worry about your payment model, depending on the kind of application that you're building. But as long as you have like a login screen to your website and you can federate access to your your content based on whether or not the login has access to the thing, you can put in your own payment system and then still deploy over the web. So lot of cool infrastructure that's already built on the web that completely applies to the development of 3D on the web. A lot of tools, a lot of libraries, good development environment, good debugger support, good mobile debugger support. You can connect your Android phone to your PC and debug with, you know, the other debugger. It's amazing, okay, amazing stuff. So, I don't really want to talk about this. Does anybody care if I skip over? There's another effort to put Vermal back in the web browser, declarative 3D for the web. Not to denigrate it in any way. I'm not a big fan of going in that particular direction because I think that it shovels a lot more code into the web browser that doesn't really belong there, but there are other reasons for doing it, like accessibility, and, but I'm not an expert in this area, so I prefer to focus on the WebGL stuff. So Khronos is actually contributing more than just WebGL into the web ecosystem, and the next couple of slides will talk about WebCL. But I think that there actually is an opportunity to develop the low-level APIs in parallel with the ones that bind those low-level APIs into JavaScript. That's what WebGL does, but OpenGL ES2 previously existed, and so WebGL was a natural binding of that functionality up into the web. There are other specs that Khronos develops, like OpenCL, like OpenSL for sound, like OpenCV for computer vision, like stream input for pulling in like every kind of device under the sun into one nice unified API that's semantically driven. And there are lots of opportunities for exposing more of this functionality that is on the native PC up into the web ecosystem. And the Khronos group is working very well, I think, with the W3C on WebGL, on typed arrays, and on other collaborations. So I personally look forward to more of this. So I'm going to breeze through the WebCL slides here, but basically, in addition to being able to do 3D graphics with your web page, with your PC, the graphics processor has been repurposed to be more of a general purpose processor. So you can upload little snippets of C-like code onto it and do actual computation, like physics simulation, for example. And that's what OpenCL provides, an industry standard way of doing computation using your graphics chip. And I mean, there's not much more to say about it. It basically lets you write really high-performance kernels that run everywhere because all of the graphics devices are supporting the OpenCL, base functionality. So the ability to compile these C-like kernels and run them on your device, even if it's a mobile phone, that behavior is specified across the industry. So WebCL is an initiative that Khronos is working on, and actually the first draft of the spec just came out, like within the past week. So I encourage you to go take a look and provide feedback to the working group. But basically, it exposes OpenCL to JavaScript. So OpenCL has specified behavior across a wide range of devices, and that is the key property that's necessary in order to expose it to the web, because the web works the same everywhere, so you need your compute environment to work the same everywhere. WebCL brings the lowest level primitives for accessing the graphics card as a compute device to the web. And that lets you do some pretty cool stuff. You could actually write new languages for the web that are auto-parallelizing and host them on top of WebCL. So it can be a new building block for dramatically extending JavaScript in new directions. It's pretty cool. So I recommend that you check it out and try out the prototypes that have been developed by Samsung and by Nokia. So I'm going to skip through this. The slides are all available, by the way, so you can go back and refer to these. But I do want to show one demonstration from Samsung. This link, this YouTube page, is linked from the slides. But basically, this is the this is a cool little. I'm going to leave the sound off and talk over it. It's a cool demo of Samsung's WebGL implementation running in the browser. They do two comparisons. First, they make a deforming model, okay, that is doing all sorts of physics simulation, and now the simulation is off, okay, and the next thing they're going to do is turn on the simulation, and it's going to be running in JavaScript, okay. Okay, so they're getting like 1 frame per second, or 1 frame every 2 seconds, okay? Something like that, maybe 2 frames a second, not very fast. And the reason is that this is a really hard problem for the CPU to compute. It's a problem much better suited for the GPU, which has massive parallelism. So this part of the video shows their WebGL prototype doing the physics simulation of these deforming bodies. And you see its interactive rates. It's like 100 frames a second. So you can get massive speed-ups by taking advantage of the floating point performance of the graphics processor from JavaScript, depending on your application. So not much more to say about that. There are definitely areas where, or fields where this kind of ability is a huge, huge win. So that's what WebGL is aiming to provide. Going forward, you can envision really cool stuff going on. You can envision video input coming in via OpenMax, or actually maybe just by WebRTC. But basically, one way or another, you get your video frames in from the camera. And you feed it into the OpenCV computer vision library to do object finding and tracking. And then you feed it into your JavaScript code, which does some sort of 3D model of the scene that it's looking at, does an overlay of some 3D graphics on it, and then uses WebGL to compose the video with the 3D overlay. And then you can take your tablet and look around at the world and see, the subway station is in that direction, or free pizza in the kitchen, or all sorts of useful information. Where's the bathroom? And I think that the web would actually be an ideal platform to develop these kinds of applications in, and it's becoming increasingly possible. So with that, I'm going to just ask everybody to get involved in the development of these specifications, especially, if you have interest in 3D graphics, please join the WebGL public mailing list and at least watch the discussions, if not participate. We're improving the, we're fixing corner cases in the spec every day. We're developing, not developing, but let's say that we're pulling in new functionality from the desktop 3D graphics environment to, in order to increase the kinds of visual effects that you can do with WebGL. And the entire ecosystem is evolving quite quickly, and it's actually really exciting to see as multiple web browsers implement new features. You can see demos coming out just every day. So I want to show some demos and point out, by the way, that there are at least 2 mobile browsers today that support WebGL. It's Opera Mobile and Firefox on Android, and I fully expect more mobile browser implementations to support WebGL in the near future. Actually, RIM Playbook is the 3rd. So anyway, with that, let me pull up a couple of demos, and let me call for questions. If anybody has a question, please just raise your hand, interrupt me. Please, back there. That's a good question. The question was, when can we expect WebGL to show up in real browsers? I don't have a prediction for you on that, but what I would suggest is join the WebGL public mailing list, provide feedback on the API, and help the working group move it forward to a point where the spec and its security properties are specified well enough that we all feel confident in deploying it. These are the main issues. Another issue is that, so we've seen how WebGL was implemented on top of this Angle graphics library, and Angle provides OpenGL ES semantics on top of Direct3D. If you assume that the target that you're going to be hosting WebGL on top of is actually direct compute as opposed to OpenGL on Windows, you may need, some work may be necessary there. More minds thinking about that particular issue would definitely help accelerate the deployment of the spec. So if you have any experience in that area, I would highly encourage you to get involved. Question up here. Okay, so this is a question and a point. The question point was that I was advocating using WebGL as the mechanism for deploying onto mobile devices, but since mobile browsers aren't really supporting it yet, it's not really viable to replace doing an App Store deployment. I expect this to be the year of WebGL on mobile. There are already 2 browsers supporting it. Actually, there's more than 2. NVIDIA has released a WebGL implementation on their Tegra hardware that supports Android that is really, really fast. They spent a lot of time getting the composition architecture to be fast so they could get the WebGL content to the screen very quickly. And so the point was that WebGL can't really replace these mobile app stores yet, and that is true. Okay, but if your time horizon for the development of your content is something like 6 months, I think it would be safe to target WebGL as how you write your app, so that with the expectation that maybe 6 months from now you're going to see a wide range of browsers supporting WebGL on mobile. That's a personal opinion. I can't promise release dates or anything like that, but given that WebGL was specifically designed to run on mobile devices, I think that this will be the year that happens. It's been a bit of a difficult road getting to a certain point of conformance and cross-browser and cross-platform behavior on desktop machines, but the mobile devices were specifically designed for this form of the OpenGL API. So I think that it'll be easier to get it running on mobile devices now that we have all of this infrastructure in the browsers for doing it on the desktop. All right, I think I should probably give you guys a 15-minute break. So thanks for coming, and look forward to seeing you again soon. Bye.